Here's a problem that involves universal gravitation and orbital motion. Mars' orbit has a diameter 1.52 times that of Earth's orbit. How long does it take Mars to orbit the Sun? So the idea here is Mars is further out, so we might actually write Earth's orbit like this and Mars's orbit like this, both of us going around the Sun here within the center. So we have Earth's orbit and we have Mars. I suppose I should write out Earth. And then of course we've got our Sun. Now the relationship between the radii of these orbits around the Sun and the time it takes to go around one full revolution around the Sun is just Kepler's third law. And it is written in terms of capital T, the period of the orbit in time, in seconds. That period in seconds squared is equal to 4 pi, the radius of the orbit cubed, all divided by the universal gravitational constant capital G, and the mass of the central object about which these planets are orbiting. In this case, that's the mass of the Sun. Now we're interested in how Mars's orbit, well, we're interested in how long it takes Mars to orbit the Sun, knowing its relative radii, which we can get from the diameter with respect to the Earth's. Now we could plug in all the numbers, we could look up the values of the specific values to get this answer, but what we really want to do is, based on what we know about the Earth, take a ratio and solve this problem by looking at the ratio of the orbital time periods between the Earth and Mars. So let's write this expression for Mars. The Mars period, little m squared, is equal to 4 pi its radius, Mars, cubed, over g times the mass of the Sun. And for Earth, similarly, we have the period for Earth's orbit squared is equal to 4 pi the radius of the Earth orbit cubed over gm Sun. Let's take the ratio of these two periods. T Mars over T Earth squared. All of these constants will end up canceling, and we're left with R of Mars cubed over R of Earth cubed. So we can see that if we take the square root of both sides and we head over in this direction, we can see that the period of Mars's orbit over the period of the Earth's orbit is equal to 3/2 the ratio of the two radii. The radius of Mars over the radius of Earth. All we've done is taken the square root of both sides. So, since we know that the diameters are related to by 1.52, the radii are related by 1.52 also. So we recognize that the Mars orbit has a diameter 1.52 times that of Earth's. So we end up over here with the time period of Mars, the time period of Earth. That ratio is 1.52 to the 3/2. Well, I'll take this a little bit and we'll make this a little smaller so we can make some more room here. So coming down here, the period of Mars is equal to 1.52 to root to the 1/2 times the period of Earth. And if we write in 365 days, and the value for 1.52 to the 3/2, which is 1.87, giving a grand total of 684 days. As the orbital period of Mars. It kind of makes sense. Mars is at a larger orbital radius. It thus takes longer for it to complete a full revolution around the Sun. Now in this example problem of orbital motion, we used a couple different math skills. The predominant one was understanding that we could, knowing something about one situation and the universal law, we could set up a ratio and find out a relationship between two other things based on what we did know. So one math skill here was being able to recognize that and to set up taking the ratio of these two planets and their orbits relative to one another to solve for one. Another thing we had to feel comfortable with was being able to understand exponents and taking the square root of both sides and following along the rules of manipulating equations that involve exponents. So take a chance to look at the recommended modules, practice some of these math skills, and then come on back and do a do-it-yourself problem involving orbital motion.